Welcome to this explainer. Have you ever stopped to wonder how a massive commercial truck shifts those incredibly heavy steel gears in literally a fraction of a second? Well, today we're going to use this really cool cinematic X-ray vision approach to find out exactly how it happens. We're diving deep into the Mercedes powershift system. It is an absolute masterpiece of electro-pneumatic engineering, and we're going to break down the invisible forces that make the whole shebang work.
Here's our roadmap for today. We'll hit 5 key stops. 1. Robot driving a manual. 2. Meet the hardware. 3. Anatomy of a shift. 4. The power of air. And finally, number 5, when shifts go wrong. Let's get started.
Starting right off with Section 1, robot driving a manual. Let's completely flip how we think about an automatic heavy-duty truck.
I absolutely love this quote from our source material. A robot driving a manual transmission. It really hits the nail on the head. See, when you climb up into the cab of a modern Mercedes Actros, you look down, and there's no clutch pedal, no traditional gear stick either. But, and here's the wild part, underneath it all, hidden inside the casing, is actually a traditional heavy-duty manual gearbox. It's got a real single-plate dry clutch and these massive, heavy-duty steel gears.
So what do we call this setup? It's known as an automated manual transmission, or AMT for short. Basically, it takes away your physical foot pedal and hand shifter and swaps them out for just a small electronic switch right on the steering column. So instead of the driver's muscles doing all that literal heavy lifting, a computer uses precise electrical voltage to trigger a giant relay circuit. That circuit uses electronics to command compressed air, which then actually slams those huge gears into place. And honestly, it does it way faster than a human ever could.
All right, moving on to Section 2, Meet the hardware. Let's see how this incredible system builds a bridge between super delicate computer signals and raw mechanical force. We can really break this down into 2 distinct halves, the brain and the brawn. The brain operates on a low-voltage 24-volt electrical system. The star of the show here is the Transmission Control Module, or TCM. This thing is constantly thinking. It's reading engine speed, road speed, throttle position, even whether you're going uphill or downhill. It also uses these Hall effect speed sensors, which are basically like little magnetic eyes, to watch exactly how fast the internal shafts are spinning. But a tiny 24-volt signal can't exactly move heavy steel. That is where the brawn comes in. The TCM sends its electrical whispers over to the solenoid valves, which act like translators. These solenoids unleash the real muscle, 10-bar compressed air. This highly pressurized air fills heavy-duty pneumatic shift cylinders, and they physically force the shift forks to move inside the gearbox. Which brings us to Section 3, Anatomy of a Shift. Okay, I want you to picture this. Let's drastically slow down a split-second shift on a steep hill. Imagine we have X-ray vision looking right into the gearbox, watching the internal magic happen in a cinematic step-by-step sequence. First, let's zoom in close on the brain. The truck is lugging up a steep hill in 6th gear, and the TCM decides, hey, we need a downshift right now to keep our momentum. So it talks to the engine over the CAN bus network, think of that as the truck's internal nervous system, and basically says, cut the power for just a split second, so the gears don't jam under the heavy load. Picture a glowing 24-volt electrical signal pulsing out of that TCM, racing down a thick, braided wiring harness, literally illuminating the copper wires inside as it shoots toward the gearbox. Next up is the electro-pneumatic conversion. That glowing 24-volt pulse reaches a heavy-duty solenoid valve block mounted right on the side of the transmission. Imagine the exact moment that voltage hits the solenoid coil. You get this sharp, metallic click as an internal magnetic plunger violently snaps upward. And instantly, a massive wave of high-pressure compressed air, picture it as this rush of glowing blue energy at 10 bar, just explodes through the newly opened valve. The electronics have successfully commanded the air. And finally, the mechanical force takes over. That glowing blue compressed air blasts into a thick pneumatic actuator cylinder. The sheer, sudden pressure forces a heavy steel piston forward, which drives a solid brass shift fork. That fork forcefully slides a massive steel gear cog right along a splined shaft. Now, because the computer perfectly matched the engine speed, the teeth of those huge gears seamlessly lock together, with a heavy, deeply satisfying mechanical clunk. The glowing electrical signals fade out, maybe a few sparks of static electricity flash across the metal, and the gears spin rapidly, transferring all that massive torque. And the craziest part? That entire sequence happens in less than a single second. Absolutely mind-blowing.
Let's move to Section 4, the power of air. Now, you might be wondering how those pneumatic muscles compare to other heavy machinery systems. It highlights a really crucial design choice. So why does this massive machine rely on highly pressurized air to slam its gears into place? Why not use a hydraulic fluid system, which is what we usually see doing the heavy lifting in large machinery? Well, this just brilliantly shows off the elegance of commercial truck design. As we can see here, heavy commercial trucks already have a massive onboard compressed air system to run their air brakes and suspension. Rather than reinventing the wheel, the engineers just tapped right into it. The air gets routed through a pressure-reducing valve to step it down to a safe 8 to 10 bar. Using this existing air supply is way cleaner, it's incredibly powerful, and honestly, it's just vastly easier to route through solenoid valves than plumbing an entirely separate, heavy, and super complex hydraulic fluid system just for the transmission. All right, let's wrap things up with Section 5, when shifts go wrong.
This system is incredibly robust and elegant when everything is perfect, but, trucks live in their real world, full of dirt, massive vibrations, and millions of miles of driving. According to auto electricians, if a driver complains that the truck is feeling jerky or it's constantly hunting for the right gear, it's almost never the heavy steel gears failing. Actually, scratch that, it's basically never the gears. Instead, technicians usually have to chase the communication lines. It could be a faulty Hall effect position sensor. These sensors are supposed to confirm a gear is fully engaged, and if they feel the TCM computer is basically flying blind and won't let the clutch re-engage. Or maybe it's a sticky or leaking solenoid valve, meaning that glowing wave of blue air pressure doesn't reach the cylinder quite fast enough. Or simply, corroded electrical connectors at the actuator plug might be completely blocking that vital 24-volt pulse from ever reaching the valve in the first place. This entire system is just such a brilliant illustration of the raw power of electro-pneumatic engineering, taking the super delicate logic of a computer and translating it into earth-moving mechanical force. It leaves us with a fascinating final thought to ponder. If a digital brain and air-powered muscles can flawlessly shift massive steel gears under thousands of pounds of load, doing it faster and smoother than a human hand ever could, what complex, heavy mechanical task will this technology automate next? Thanks so much for joining me on this explainer, and I'll catch you next time.